Hello everyone. In our last session, we discussed about some of the research study designs used in medical research. In today's session, we'll discuss about some of the tools they are used to quantify the risk in the observational studies. Now, let's briefly review what we learned in last session about the observational studies. There are three types of observational studies: cohort study, case control study, and cross-sectional study. And cohort study could be prospective and retrospective, and based on type of the observational studies, we use different type of tools to quantify the risk. When the outcome is a qualitative variable, or when the outcome can be categorized or can be presented in the group, such as male, female, or labels like small, medium, or tall. So if the outcomes are qualitative, then the best way to represent the data variables to qualitative variables is through the contingency table. And contingency tables, you can represent the numbers appear in each categories. And whenever you are dealing with the qualitative data or the data with the categories, always we represent the data in terms of the numbers, means the frequency. And the percentage and frequency are the two major things we are always looking for the qualitative data. And we can use this contingency table to calculate other risk quantifying tools such as relative risk, attributable risk, or the odds ratio. All these tools are used to quantify the risk, and they are used to compare between two or more groups. And what do you want to calculate, whether odds ratio, relative risk, or attributable risk? The calculation of these tools are based on what kind of study you are doing. If you are doing cohort study, you can use odds ratio, attributable risk, and relative risk. And if you are using the case control study, then you can only use odds ratio and attributable risk. We'll discuss how do we implement these kind of tools and what are the requirements to implement these tools in the next few slides. As we already discussed, in cohort study, we observe the cohort of exposed and non-exposed, and then we want to see them how many of the cohort, those how many in the cohort develop the disease. So cohort studies are, they have the temporal framework, means we always observe the cohorts of the exposed and non-exposed, which can be considered as the risk factors of the disease, and then among those risk factors, how many develop the disease. So in cohort studies, they could be retrospective or prospective, and we can use both odds ratio or relative risk or risk ratio in cohort study. Now, first, let's discuss about the risk ratio. The risk quantifies the chance of experiencing the outcome of interest in a given population, and a relative risk, sometimes it is also called the cumulative incidence, is the ratio of risk in between exposed and unexposed groups. So here's an example. Let's assume that your contingency table is presented this way, where you have smoker and non-smokers in rows, and then disease status present or absent in the columns. And here this A indicates the number of smokers who has disease, and similarly B represents the number of smokers who didn't have the disease. And similarly you can also represent non-smokers. Now in this table, what is the risk of developing disease among smokers? Because smoking is an exposure factor, okay, and this is a non-exposure factor. So what is the risk of developing disease in among smokers? It is A out of, the denominator will be A plus B. So out of total A plus B, A of them develop the risk of disease. And similarly for non-smoker, it is C out of C plus D. So the relative risk is nothing, it's just the risk ratio of these two risks. The risk of disease among smokers versus risk of disease among non-smokers. Once you calculate the relative risk, then how do you interpret this relative risk or the risk ratio? You can interpret this risk ratio as the risk of disease among exposed group, which is this value here, RR times relative risk times the risk of disease among the unexposed group. So we are just comparing exposed versus non-exposed group. And think about the situation where the risk of disease is same in the both cases. In that case, what could be the value of the relative risk? If the risk of disease is same on both exposed and non-exposed group, then the value of the relative risk will be 1. And in that scenario, if relative risk is 1, then there is no association. And if you are calculating the confidence interval of relative risk, and that confidence interval contains 1. Think about that. In confidence interval, there are two values, okay, lower limit and upper limit, and everything in between those two limit values are the possible values. And if the confidence interval contains 1, there is no association. And in that case, risk in exposed is same as that risk in non-exposed group. And we can say that there is no association between the exposure factor and the disease factor. And if the relative risk is more than 1, it means that the risk of exposure in exposed group is higher compared to the risk of disease in the non-exposed group. And we call this a positive association, means the exposure is causing some impact on the disease. And if the relative risk is less than 1, which means all the values in the confidence intervals are less than 1. And that time we can assume that there is no risk of exposure factor. Instead, the exposure factor has a protective effect, means when you are dealing with the drugs, and drug has a protective effect in the disease because it protects our body from the disease. And so in case of the drug, if you find relative risk less than 1, it means that it has the protective effect. And it means that the risk in the exposed group is less compared to the non-exposed group. You can think this as a risk in the treatment group compared to the risk in the placebo group. And this is also called the negative association. Similarly, you can also calculate the odds ratio. Odds ratio can be calculated in both prospective and retrospective studies, but relative risk can only be calculated in the prospective study. Understand that this relative risk, it is only for the prospective study or the forward-looking study, but the odds ratio can be calculated in both prospective and retrospective studies. Odds ratio is the ratio between the odds. Relative risk is the ratio between the risk, while odds ratio is the ratio between the odds. So what is odds? Odds provide a measure of the likelihood of a particular outcome. They are calculated as the ratio of number of events that produce that outcome to the number of events that do not. Let's see this example here in the similar contingency table here. If you want to see the odds of disease among S group, then this is A over B. Because among X group, A of them has disease and they don't have disease. So it is just the ratio between disease versus non-disease cases. And among the exposure group, non-exposure group, then the odds of disease is C over D. And if you take these two odds, if you take the ratio of these two odds, A over B divided by C over D, then this is called the odds ratio. And in short form, if you manipulate this little bit, then you can see that this cross multiplication diagonally gives you the odds ratio, A times D divided by B times C. That's what it is. And we can interpret the odds ratio in similar way as in the relative risk. But when you are interpreting odds ratio, make sure that instead of saying probability or the risk, you are saying it's the odds. So odds of disease among exposed group is K times the odds of disease among the unexposed group. Here is an example. Odds of lung cancer among smoker is 2.5 times that of the non-smoker. And if there is a significant odds ratio less than 1, then it's wise to take the reciprocal and interpret for the altered group. So what does that mean? So let's discuss in the next slide. When the odds ratio is less than 1 or in the fraction, then it's really hard to interpret that. And to interpret the odds ratio less than 1, it's always wise to take the reciprocal of that odds ratio and then make the interpretation for the altered group. For example, here, if the odds of a disease for a group A is 0.6 times that of group B, then this 0.6 times makes a little bit confusing. So instead of interpreting this odds ratio of zero point 0.6, what we do is we take the reciprocal of that, okay, and then then the odds of, instead of saying odds of disease for group A, we say it is for the group B because we altered that group. So odds of disease among group B is 1.67 times that of group A because group A has smaller odds, and we take the reciprocal here. And if the odds ratio contains 1, if the odds ratio is 1, or if the confidence interval of the odds ratio it contains 1, it means there is no association, means there is no difference in odds between two groups, and exposure is not related to disease. If odds ratio is more than 1, it means that the exposure has higher odds of getting the disease, and it is also called the positive association. And similar to the previous one, if the odds ratio is less than 1, it means it has the protective effect, and we call it the negative association. Now let's discuss another risk factor that is used in both cohort study and case control studies, or both prospective and retrospective studies. Now, this is called the attributable risk. Attributable risk means it is the risk that is attributable to the exposed factor only. So, let's see this example here. Let's see this pictogram here. So, this the first bar, it shows that the number of disease cases among the exposure case, and this second bar is the non-exposure group, and these are the disease cases. And we know that both exposed group and non-exposed group, they will have disease. Okay, so it's not that when the subject is not exposed to some factor, he will never get the disease. It's not that like that. Even the non-smoker could have lung cancer. So now it's the same case here. Now our goal is to see that, because when this is non-exposed group, this is exposed group, and up to this line here, these are called the common factors. Okay, these are called the common factors for the disease. So no matter whether it's an exposed group or the non-exposed group, there are some common factors on both cases, and because of that it causes disease. And now we want to see how much attributable risk is there in the exposed group that can cause the disease. In other words, it tells us how much risk is only associated with the exposure and what is the actual contribution of the exposure to the disease. That's what attributable risk. So if you see this carefully, if you subtract this risk here, the common risk, from the risk of the exposure, then you can get the attributable risk. So it is just the incidence in the exposed group minus incidence in the non-exposed group. Incidence means it's the risk. So in the exposed group, the risk is A over A plus B, minus in non-exposed group C over C plus D. So if you subtract these two risks, then you will get the attributable risk. So attributable risk in the exposed group equals the difference between the incidence in the exposed group and the incidence in the non-exposed group. Now let's see this example here. This example shows the coronary heart disease status and the smoking status. So you can see smoking and the rows and the status of the coronary heart disease in the column. And now if you want to calculate how much disease or how much CHD is attributable only to the smoking, you can calculate the attributable risk. So to calculate the attributable risk, first you find the risk of disease among smokers, which is 84 out of 3000, and the risk of disease among non-smokers is 87 out of 5000. So if you subtract this risk on the non-exposed group from the exposed group, then you can get the value which is the attributable risk for 1000 population. I calculated here for 1000 population. And now this means 10.6 incidents per thousand are attributable to the smoking only. You can also calculate the percentage of the attributable risk, which is nothing, it's just take the attributable risk here and divide by the risk and the exposed group, which is 28 here, and take the percentage. Okay, this means that among exposed group, 37.86% are attributable to the smoking only. So this is only in the exposed group. You can also calculate attributable risk by using the relative risk, because attributable risk is based on the relative risk. When you subtract this relative risk, then you can get the attributable risk. Here is a relationship you can use if you want. Attributable risk percentage is relative risk minus 1 divided by relative risk. Now, odds ratio, attributable risk, and relative risk are the three major tools we use to quantify the risk. Odds ratio and attributable risk can be used in both prospective and retrospective studies, while the relative risk can only be used in the prospective study. Now, based on these tools, we can also have some other derived tools. Relative risk reduction is a derived unit, and we can get the relative risk reduction when relative risk is less than 1, and it shows us the reduction of risk attributable to the drug in the treatment group. And as I said, this relative risk reduction is nothing, it's just the 1 minus RR, and RR relative risk must be less than 1. And we only calculate relative risk reduction when the intervention has a protective effect, means when we are using the drugs to treat the disease. Now here is an example. If the relative risk is 0.3, then the relative risk reduction is 70%, means drug reduce 70% of disease risk among the treatment group. That's how we interpret this. And another derived measure is absolute risk reduction, and this is useful when relative risk is less than 1. Attributable risk reduction or absolute risk reduction, you can think this is a difference in percentage of risk between treatment and placebo group. So it is very similar to the attributable risk, but instead of taking the risk in treatment minus risk in control, we are taking the risk in control minus risk in treatment, means we are just altering this. So it's a very similar thing as a attributable risk, but it is only applicable when relative risk is less than 1, or when there is a protective effect of the drug. For example, if 5% of people who receive COVID-19 vaccine, they develop COVID-19 compared to 24% of the people who receive placebo, it means this vaccine has protective effect against the COVID-19. Then the attributable risk here, or the absolute risk reduction here, is 24% minus 5%, which is 19%, or 0.19, means 19 per 100. And it is important that you only use relative risk reduction and absolute risk reduction when relative risk is less than 1. And remember that this RRR, or relative risk reduction, is a counterpart of RR, or relative risk, and absolute risk reduction is the counterpart of attributable risk, or AR. Another derived measure is number needed to treat. When the relative risk is less than 1, then there is a protective effect of the drug, and in that time we want to see how many patients we need to treat so that one patient will benefit. So this is called the number needed to treat, and number needed to treat is nothing, it's just the ratio of attributable risk reduction. So lower number indicates better treatment. For example, in previous case, if we have attributable risk reduction is 0.19, so 1 over 0.919 is 5.26. So it means that almost 6 patients they needed to treat for one patient to benefit. And as I said, the lower number indicates better treatment, means if you need to treat less number of people for one person to benefit, that is better. And always use NNT or number needed to treat when relative risk is less than 1 or when the drug has the protective effect. And number needed to harm is very similar to number needed to treat, but you can use this when there is no protective effect and then when there is a risk, a relative risk more than 1. And number needed to harm can be derived is how many patients needed to expose in the risk factor so that one patient will be harmed. And higher number indicates less risk or safer exposure. For example, in a previous example of attributable risk, we have 0.10. If you go back here, we have attributable risk 0.10, okay, 10.6 in terms of, this is for 1000. So if you convert this into 1%, it will be 0.10. And then if you divide this by 1, then you will have number needed to harm or NNH. And this means 10 people needed to expose for smoking for 1% to get coronary heart disease, cardiovascular disease. And you use NNT only when relative risk is more than 1. Now, let's look at this example. In these examples, we want to see whether the low dose aspirin was beneficial in reducing the myocardial infarction among the physicians, male physicians. So the study population, it consisted of 22,000 male physicians, and they were randomly assigned to one of these groups, aspirin and placebo. And then we take the data, and here is the summary of the data. So 139 physicians who took aspirin, they had MI, and similarly 10,898 who took aspirin did not have MI. And these are the numbers for the placebo group. Now, here, if you see here, okay, these physicians, they were randomly assigned to these treatment groups and they were followed for a certain period of time. So this is a prospective and cohort study because we have two cohorts. One is the exposed cohort or the treatment group. One is the placebo group or the control group. So we have two cohorts and then we follow them. And now, since it is cohort study and it is a prospective study, we can calculate odds ratio, relative risk, and attributable risk. All three can be calculated here. Okay. So let's calculate the relative risk here. Relative risk is the number who got disease among the exposed group or the treatment group. These many got the disease out of this 11,037. So that is what the relative risk of disease among aspirin. So it is protective. It is less than 1. This relative risk is less than 1 means it's a protective effect. It has the aspirin has protective effect on MI. Similarly, you can also calculate the odds ratio, which is 0.58. And in both in here you can see that both of these are less than 1. So when you interpret these, it's hard to interpret this less than 1 fractions. So you just take the reciprocal and interpret them for the placebo group. Since there is a protective effect, we cannot calculate AR or attributable risk. Instead, we calculate attributable risk reduction, which is the risk among placebo minus risk among aspirin. So this is 9 per thousand is the attributable risk reduction for aspirin. Now, here is another example. 5% of patients who received Moderna COVID-19 vaccine, they developed COVID-19, while 36% of patients without COVID-19 vaccine developed COVID. Now, what is the relative risk of COVID-19 among those who received vaccine? So, how do you calculate the relative risk here? If you want to calculate the relative risk is the ratio of risk between exposure and non-exposure, and our exposure factor is the vaccine here, or the treatment is the exposure factor in this case. So this is just the ratio of these two percentages. So the relative risk is 5 out of 36, which is 0.14. Now, what does this indicate? Since this is less than 1, so there is a protective effect of the COVID-19 vaccine. So the risk of developing COVID-19 among those who got Moderna vaccine is 0.14 times. But this is less than 1, so we need to take the reciprocal and interpret that. So what we can do is the risk of getting COVID-19 is almost 7 times, because 1 over 0.14 is 7 times compared to those who got COVID-19 vaccine. So you can interpret this way. Now, since relative risk is less than 1, then we can calculate relative risk reduction, and which is 1 minus RR. This means Moderna vaccine is responsible for reducing the risk of COVID-19 more than 86% of times. It's very good. And similarly, you can also calculate the attributable risk reduction, or ARR. This can be written as just the difference between 36 and 5, which is 31%. Means Moderna vaccine is attributable to the risk of COVID-19 by 31%. How do you calculate the number needed to treat? Since relative risk is less than 1, we can calculate number needed to treat, and number needed to treat is reciprocal of ARR. So you can just calculate 1 over 0.31, which is 3.225. This means almost 4 individuals needed to treat for 1 patient to benefit, or you can, if you round down, it will be around 3 patients, at least 3 patients to be vaccinated for 1 patient to get benefit. So let's see another example. 20% of smokers get lung cancer, while 1% of non-smokers get lung cancer. So in this case, now, what is the relative risk of the lung cancer among smokers? So it is just the ratio of risk between exposure and non-exposure group. So the exposures, they have 20% risk, and non-exposure have only 1% risk. So it is just the ratio of 20 and 1. So the risk is 20. Relative risk is 20 per 100, since we are expressing this in terms of percentage. So 20 per 100. Now, what does this indicate? It indicates that the risk of lung cancer among smokers is 20 times compared to the non-smokers. And attributable risk, you can, since relative risk is more than 1, now you can calculate the attributable risk. Attributable risk is 20 minus 9. It's just the difference between the risk among exposure and non-exposure group. And it is 19% of lung cancer risk is attributed to the smoking. Now, if you want to calculate the percentage, then you can just calculate this 19 attributable risk out of 20 in this exposed group, so which is 95%. So in the exposed group, among the smokers, 95% of lung cancer risk is due to the smoking. Now, what is reduction in relative risk? Since relative risk is more than 1, we cannot calculate this RRR. Similarly, you cannot calculate ARR. And similarly, to calculate number needed to harm, you take the reciprocal of attributable risk, and this is 1 over 0.19. And remember that this 0.19 is per unit. Okay, here we have attributable risk defined for per 100. So here we have 0.19 is per unit. So it is 1 over 0.19, which is 5.1. Means at least 5 patients they need to expose to smoking for 1 to get lung cancer. In case control study, we use odds ratio and attributable risk, and we cannot use relative risk, as relative risk cannot be used in retrospective studies, and all case control studies are the retrospective studies. Interpretation of attributable risk is very similar whether it's a case control study or cohort study, whether it's a retrospective or prospective study, but the interpretation of odds ratio is different in case control and cohort study. It's because in cohort study, we start with the exposure cohort and then we look at the disease status. But in case control study, we start with the disease status and then we look for the exposure factors. We go back and look for the exposure factors. So the interpretation of odds ratio are different. Here is the simple way to understand the interpretation is that look at this in the cohort study we say the odds of disease, and in case control study we say the odds of exposure. And here is an example to better understand this situation. If we have this odds ratio is calculated as 2.5 for both case control and cohort study, and then if it were the cohort study, then we can interpret this odds ratio as the odds of lung cancer among smokers is 2.5 times that of the non-smokers. So smokers are more likely to have lung cancer. If in the same case, if it were the case control study, then instead of saying odds of lung cancer, because we don't have odds of disease here, but we have the odds of exposure. So we can say that the odds of smoking, which is exposure among lung cancerous individual, is 2.5 times than that of the non-lung cancerous individual. Means there is a higher risk of exposure or the smoking. So the smoking is more likely to associate with the lung cancer. That's how we interpret the odds ratio when it is a case control and cohort study. And here is the summary of this odds ratio and relative risk. Odds ratio can be calculated in a cohort study and in a case control study, but relative risk is only calculated in the cohort study, the cohort and prospective studies. The exposure of odds ratio is equal to the disease odds ratio. Understand that the exposure in our previous case here, this odds ratio, the value is 2.5, whether it is for the exposure or for the disease. In general, we use odds ratio compared to the relative risk, because when we assume that the cases and control, they are the representative of the entire population, they are unbiased sample, then we always recommend it to use odds ratio. And relative risk can only be calculated in a cohort study, and as I already mentioned, and it can only be used in the prospective cohort study. And odds ratio is similar to the relative risk if the disease is rare. Another type of observational study is a cross-sectional study, and cross-sectional studies, they are very useful in looking at the trends, and it is just a snapshot of a data at a time point. So you can think this cross-sectional study is just the overall picture of a data at one time point. And so in cross-sectional study, we usually calculate the percentage or the prevalence, and percentage is just the number of events or the disease cases at some time points divided by the total population at that time point. So it's just the overall picture at a certain time point, and we are not looking at any other factors at this point. Here is an example. A measurement of cancer is taken in a population of 50,000 people, and it is found that 1,300 were recently diagnosed with cancer and 4,500 are living with cancer. So if you want to see here, then the prevalence is 4,500 plus 1,300 is the total cancer case divided by the total population, that is 50,000. So it is 116 per 1,000. Another useful measure to use in cross-sectional study is the incidence rate. While the prevalence is the number of all existing cases of a disease in a population in a certain time period, Incidence is the number of new cases of disease that developed in a population during a defined period. So you can think prevalence is describing a pool of disease in a population, while incidence can be described as the input flow of a new disease into that pool of disease. So the total burden of a disease at one point of a time can be considered as a prevalence, while the rate of particular disease at a certain time can be considered as incidence. So in general, you can say that the prevalence can be written as the overall incidence at certain time times the how long the incidence is happening. So duration. So you can think this is a bathtub. The overall water in a bathtub at certain time point is the prevalence, while the amount of water coming through the tap is the incidence. Here you can compare incidence and prevalence in different ways, and I have taken this reference from the Mosner and Kramer's textbook. And incidence is a probability of developing a disease because it is all new cases, and prevalence is the chance of already having the disease because it accounts the past existing disease as well. And in incidence, when you calculate the incidence, your numerator is always only the new cases. It doesn't count any existing cases. And for the prevalence, it counts both new and old cases. Incidence requires a follow-up individuals in a population because we need to identify the new cases. Without follow-up, new cases couldn't be identified. And for prevalence, it is not always necessary to have the follow-up, and sometimes all existing cases can also give the prevalence. Incidence does not depend on the duration of the illness as it is only based on the new cases. But prevalence, it depends on the all previously existing disease cases or how long the person is in the disease. Longer the person is in the disease status means there are more people and the prevalence will always be higher. And also, incidence is a preferred measure when studying the cause and effect because incidence is uh, based on new cases at certain time points. So it is very useful to identify the causal effect. And for prevalence, it is a preferred measure when estimating the population-based burden of the chronic disease or attribute of the disease to the entire population. Here is an example of how to calculate the incidence rate. Calculation of incidence rate is a little bit complicated. Is you need to calculate the total person time, and I do not expect you to know all these calculation, but I expect you to know the calculation of relative risk, odds ratio, odds, attributable risk, and other derived measures such as RRR, ARR, NNT, NNH, because you may need to know them for your step 1 exam. Let's assume that we have a population of 250 and we followed them for 10 years, and we find that after at first there were 35 individuals who already have HIV, and then after 5 years we diagnosed 30 more individuals, and after 10 years we diagnosed 40 more cases. And in that case, if you want to calculate the prevalence rate, prevalence is just the overall rate. Okay, it is pretty easy. Just take all total number of cases, which is 35, 30, 45. You add them and divide by total number of population at risk, which is 250. So that is the prevalence rate. Now, prevalence rate only tells you the overall picture. It doesn't tell you how many are at risk in every year, okay, or per person year. How many are at risk? It doesn't tell you. So to get that information, you need to calculate the incidence rate. And to calculate the incidence rate, first you need to identify how many new cases were there. Total, there were only 70 new cases because 35 were already existing when we started the study. So it is not counted. So only 70 new cases were there. Now you need to identify the total person year who are at risk of disease. So think about this. These 30 individuals, we assume that even though we diagnosed at 5 years, we assume that they have developed HIV somewhere in between these 0 to 5 years. And the best number, best time for that to represent this 0 to 5 years is 2.5 years. So we assume that these 30 individuals up to this 2.5 years, they were at risk of developing HIV. So that's why the total time point is 30 times 2.5 for each person. Okay, one person is at risk for 2.5 years, so 30% person they were at risk for 30 times 2.5 years. Similarly, these 40 individuals, they developed disease at 10 years. They were diagnosed at that time, but we assume that they might have developed the disease between 5 to 10 years. And the best way to represent that time between 5 to 10 years is 7.5 years. So we assume that these 40 individuals were at risk, means they did not have disease until 7.5 years. So it is total time person year is 40 times 7.5. Now, the remaining individuals 145, because 145 is 250 minus 40 minus 30 minus 35. So that is 145 individuals, okay, who never had HIV. So these 145 individuals were at risk for all 10 years, means they did not have any disease for 10 years. And if you calculate these, then the total person year is 1825. Now, if you take the ratio of these two factors, then you will get the incidence rate. So the incidence rate of HIV is 70 out of 1825, which is 0.038 per person. This means 38 disease incidents per 1000 person year. And you can compare the incidence and prevalence here. The overall picture shows that there are 42 per thousand are at risk, but incidence rates show that 38 per year are at risk. Thank you very much. Our next session will be about measures of central tendency and dispersion and normal distribution, and we also discuss about some other statistical tools used in medical research. Thank you.